see which terms are going to be relevant. 1/2 mv naught squared plus k little q big Q over R1 equals 1/2 mv final squared plus k little q big Q over R final. So in this case, this last term is going to, what's going to happen to it? That'll go to 0, and the limit as R final goes to infinity. So that's 0, and this one was already 0 because we started from rest. So that means that V final is going to be square root of 2k little q big Q over R1. But R1 is just 1 meter. So can you see how that relates to this? It's going to be the square root of 2 bigger, because this is basically, well, R1 is 1 here. And here we have R1 minus 1 over 2 R1. So that's 1/2 R1. So you just see here that we're different by a factor of the square root of 2. So even though half of the energy was in kinetic here, and so that means that that kinetic energy was doubled, so why did the velocity double? Why did the velocity just go up by a factor of the square root of 2 from what it was here? Because the energy goes like the velocity squared, so doubling the energy means the velocity went up by a factor of the square root of how much the energy increased, or a square root of 2 difference. So your V final in this case would be square root of 2 times 13.42, and that was that original number that I accidentally wrote up for the wrong reason, 18 point whatever it was, 3 meters per second. Any questions? Yeah.
In the V final expression, could I divide that mass?
And then if we compare these two, we see that they're the same except for that factor of the square root of 2. Okay, so that's how you deal with an energy problem. Now, in some problems, you might want to bring a particle in. Sometimes, like in fusion reactions, what they want to do is bring a particle in from a long distance away, but then have it have a final velocity that's very close to 0 when the two particles are in close proximity to each other. The reason for that is to get fusion to happen. There are very strong forces, but they're very short range. So if you get it to just run out of energy at the right point, then these little nuclear hooks can engage. They're associated with a strong nuclear force. And so then that can allow for a fusion reaction to take place. And so there's lots of different applications of these ideas of energy as it relates to electrostatic forces. And that's just one of many, many others. The history of science, there are all kinds of things where particles would be shot in, like in the Rutherford experiment to determine the physical extent of the atom and how big the nucleus was relative to the orbiting electrons. Rutherford slammed alpha particles, which are helium nuclei, into a piece of gold foil. And then they watched the recoil effects from that. Now that's all electrostatic stuff. And it showed that for some very narrow range of angles, it would come straight back at you. And so from that, they were able to deduce that the nucleus was 100,000 times smaller than the atom. And that's where all the mass is pretty much 100,000 times small. And so that was a remarkable discovery that went kind of against your normal common sense reasoning. But again, it was determined by this kind of particle physics using this kind of energy connection. Any questions? Okay. What I want to do to finish this up is to look at how we can relate the electric fields from problems that we've already done in chapter 23 with Gauss's law. And by the way, if any of you want any help with your Gauss's law assignment that's due with our lab tomorrow, you are welcome to ask me questions during lab today or tomorrow. And glad to go over any of those with you. Not sure how far you got. I haven't talked to Dr. Beach yet. Not sure how far you got with that. I know you finished off that little Cal Poly thing that they do to get you used to the idea of Gauss's law. But then the tougher problems are the ones that weren't due until Friday. All right, so this next example, let's say we have a spherical shell, and we have charge on the surface of this conducting sphere. And then let's say we have minus Q on the spherical shell. Now, you should have been able to figure out the electric field for this using Gauss's law. And these are the kinds of problems that I gave you to kind of work on this last time. But if you're in here, your electric field E from this charge wouldn't be affected by the minus charge on the outside. So you just have E times 4 pi r squared, where r is less than b greater than a. So this is a, this is b. E times 4 pi r squared equals the charge enclosed, which would be plus q over epsilon naught. So this gives us our normal E equals kq, or q, over 4 pi epsilon naught r squared. But this is just for r less than b greater than a. What's the electric field out here? Zero, because what? Zero is charge enclosed. Good. You've got equal amount of negative and positive enclosed, and so therefore the electric field is zero. What is the electric field inside of A? Zero. And in this case, you're also enclosing zero charge because all the charge is on the surface of a conductor. So if we want to plot this electric field out versus R, it's going to be 0 up to A. It's going to go up to A and then drop off as Q over 4 pi epsilon naught R squared, and then drop back down to 0 at B, and straight out. So that's what the electric field versus R looks like for all points in space. Now, how can we relate that to the voltage? Well, we saw before that the if you know if you know V, you can get E. So what was that technique? Well, we saw before that E was equal to minus dV dr. We have a purely symmetric, spherically symmetric situation. So this is get E from V. So if we know V, we can differentiate and get E. But what if we don't know? What if we can measure V? What if I go in with voltmeter and I measure V and then I want E? Well, then what we got to do is cross multiply here, and we end up with delta V, this is AB, this is our voltage difference between A and B. Is equal to the integral from A to B of E times dr. And this is going to be the magnitude of it. So this is our general expression. The more general is VAB equals minus the integral from A to B of E dot dr. So it depends on which way you're going. If you go from positive to negative, then this is going to be a negative value because you're going with the electric field. But if E is in the same direction as R, then we can easily patch up the minus signs later, because I know if I go from negative to positive, it's going to be a positive change in voltage. If I go from positive to negative, it's going to be a negative change in voltage. And so what I'd like you to do then is to take what I have here and calculate VAB. And that'll be our in-class activity for today. You can add that in to the stuff that is due on Friday. And all of these Gauss's law things that are due tomorrow will be graded as extra credit for lab points. So these are things that I'm highly suggesting you do. And you saw before that when I had that thing in the little handout, I said do this for extra credit. That was one of the problems on the exam. For the people that did the extra credit, they were good to go on problem 2. So just keep that in mind. This is extra credit, but it is stuff that is very likely to appear in future quizzes and exams. So go ahead and see what you can do with that for a few minutes. And I won't have my usual time after class because I'm doing info meeting for the Europe tour.